Welcome to the ultimate guide on reinforcement learning, ARL. The science behind agents that learn to play games, control robots, drive cars, and make decisions in complex environments. In this video, we'll cover 200 expert-level interview questions and answers, from fundamentals and mathematical foundations to deep RL, actor-critic methods, exploration strategies, real-world applications, challenges, and the future of RL. Whether you're preparing for interviews or building cutting-edge AI systems, this is your one-stop masterclass on reinforcement learning. What is reinforcement learning, RL? Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment. It receives feedback in the form of rewards or penalties and aims to maximize cumulative reward over time. Unlike supervised learning, RL doesn't learn from labeled data, but from trial and error. How does RL differ from supervised and unsupervised learning? In supervised learning, models learn from labeled datasets. In unsupervised, they discover patterns without labels. RL is different because it learns by interacting with an environment, receiving delayed feedback, and optimizing for long-term rewards rather than immediate accuracy. What are the core components of an RL system? The main components are agent, the decision maker; environment, the world the agent interacts with; state, the current situation of the environment; action, choices the agent makes; reward, feedback from the environment. Together they form the RL feedback loop. What is the Markov decision process, MDP, in RL? MDPs provide the mathematical foundation for RL. They describe environments using states, actions, rewards, and transitions with the Markov property. The future depends only on the current state and action, not the past history. RL algorithms typically optimize policies within the MDP framework. What is a policy in RL? A policy defines the agent's behavior. It's a mapping from states to actions. Policies can be deterministic, always the same action, or stochastic, probability distribution over actions. The goal of RL is to learn an optimal policy that maximizes expected rewards. What is the difference between value-based and policy-based RL? Value-based methods, like Q-learning, learn how good each action is in a given state. Policy-based methods, like reinforce, directly learn the probability distribution over actions. Some algorithms, like Actor-Critic, combine both. What is the reward signal in RL? The reward signal is feedback from the environment that guides learning. Positive rewards encourage actions, while negative rewards discourage them. It defines the agent's goals. However, designing the right reward function is critical to ensure the desired behavior. What is cumulative reward in RL? Cumulative reward, or return, is the total reward an agent collects over time. Since environments may be ongoing, future rewards are discounted by a factor gamma, balancing short-term and long-term gains. Agents aim to maximize expected cumulative reward. What is the exploration versus exploitation trade-off? Exploration means trying new actions to discover rewards, while exploitation means choosing known high-reward actions. ARL agents must balance both. Too much exploitation risks missing better strategies, while too much exploration slows learning. What is the difference between on-policy and off-policy learning? On-policy methods, like SARSA, learn from the actions the current policy takes. Off-policy methods, like Q-learning, can learn optimal behavior from exploratory or random actions, even if different from the current policy. What is a value function in RL? A value function estimates how good it is for an agent to be in a state or take an action. It predicts expected cumulative rewards. Value functions guide decision-making by identifying which states or actions lead to better outcomes. What is Q value in RL? Q value, or action value, represents the expected return of taking a particular action in a given state and then following the optimal policy. Q-learning algorithms revolve around estimating and improving Q values. What is a model-free RL method? Model-free methods don't learn the environment's dynamics. They directly learn value functions or policies from experience. Examples include Q-learning and policy gradients. They're flexible but often sample inefficient compared to model-based approaches. What is a model-based RL method? Model-based methods try to learn the environment's dynamics, the transition probabilities and rewards. They can simulate outcomes and plan ahead, making them more sample efficient. However, they require accurate models, which may be hard in complex environments. What are episodic versus continuous tasks in RL? Episodic tasks have a clear start and end, like playing a game of chess. Continuous tasks go on indefinitely, like controlling a self-driving car. The choice affects how cumulative rewards and policies are defined. What is discounting in RL and why is it important? Discounting uses a factor gamma, 0 less than or equal to gamma, less than or equal to 1, to reduce the importance of future rewards. A gamma close to 0 makes the agent focus on short-term rewards, while a gamma close to 1 encourages long-term planning. Discounting stabilizes learning in infinite tasks. What is the Bellman equation in RL? The Bellman equation expresses the relationship between the value of a state and the values of subsequent states. It provides the recursive foundation for dynamic programming, Q-learning, and many other RL algorithms. What is a policy evaluation in RL? Policy evaluation estimates the value of a given policy by computing expected returns from all states under that policy. It helps assess how good a policy is before improving it. What is policy improvement in RL? Policy improvement updates a policy by choosing actions that maximize value functions. Combined with policy evaluation, this forms the policy iteration algorithm, where policies gradually converge toward optimal. What is the ultimate goal of reinforcement learning? The ultimate goal of RL is to find an optimal policy that maximizes expected cumulative rewards. In practice, this means training agents that can make effective, adaptive decisions in uncertain dynamic environments. What is a Markov decision process, MDP? An MDP is a mathematical framework that models decision-making problems in RL. It consists of states, actions, transition probabilities, rewards, and a discount factor. The Markov property ensures the next state depends only on the current state in action, not past history. What is the Markov property and why is it important? The Markov property states that the future is independent of the past, given the present. This simplifies modeling because agents only need to consider the current state to make optimal decisions, which is the basis of MDPS. What is a transition probability in RL? Transition probability, denoted P of S prime given S comma A, defines the likelihood of moving from state S to state S prime after taking action A. Knowing transition probabilities is essential in model-based RL for predicting outcomes and planning. What is the reward function in MDPS? The reward function R of S comma I assigns a scalar value for performing action A in state S. It defines the agent's objectives by signaling desirable or undesirable outcomes, guiding the policy toward maximizing cumulative rewards. What is the difference between deterministic and stochastic policies? Deterministic policy maps a state to a fixed action. Stochastic policy maps a state to a probability distribution over actions. Stochastic policies are more flexible and useful in environments with uncertainty or partial observability. What is the value function in mathematical terms? The state value function V pi of S is the expected cumulative reward starting from state S and following policy pi thereafter. Formally, V pi of S equals E of sigma gamma to the power of TRT given S0 equals S pi. What is the Q function in mathematical terms? The action value function Q pi of S comma A is the expected cumulative reward starting from state S, taking action A and following policy pi. Q pi of S comma A equals E of sigma gamma to the power of TRT given S0 equals S, A0 equals A pi. What is the relationship between Vs and Qs comma A? The value of a state is the expected Q value under the policy. V pi of S equals sigma, pi of a given ES times Q pi of S comma A. This means the state value is derived from action values weighted by the policy's action probabilities. What is the Bellman expectation equation? It defines the recursive relationship of value functions under a policy. V pi of S equals E of R plus gamma, V pi of S prime. This equation expresses how the value of a state equals immediate reward plus discounted value of the next state. What is the Bellman optimality equation? The Bellman optimality equation defines the value of a state under the optimal policy. V star of S equals max AE of R plus gamma V star of S prime. It forms the foundation of dynamic programming and Q learning. What is policy iteration? Policy iteration alternates between policy evaluation, computing VPI, and policy improvement, updating the policy greedily with respect to VPI. This iterative process converges to the optimal policy. What is value iteration? Value iteration updates value functions directly using the Bellman optimality equation. V of S arrow max, A E of R plus gamma, V of S prime. It combines policy evaluation and improvement into a single step and converges faster in practice. What is the difference between policy iteration and value iteration? Policy iteration alternates between evaluation and improvement until convergence. Value iteration skips explicit evaluation and directly applies the Bellman optimality equation. Value iteration is typically more efficient, though both converge to the same optimal policy. What is Monte Carlo estimation in RL? Monte Carlo methods estimate value functions by averaging returns from many episodes. They don't require knowledge of transition probabilities, but need complete episodes and can be high variance. What is temporal difference TD learning? TD learning estimates value functions by bootstrapping, updating predictions based partly on other predictions. Unlike Monte Carlo, it learns from incomplete episodes and updates online, making it more efficient in many environments. What is the TD zero update rule? The TD zero update rule is V of S is equal to V of S plus alpha times R plus gamma, V of S prime minus V of S. Here, alpha is the learning rate, and the term inside is the TD error. It adjusts the value estimate based on observed reward and next state prediction. What is the TD error? The TD error delta equals R plus gamma V of S prime minus V of S. It measures the difference between predicted and actual returns. Minimizing TD error is the core of many RL algorithms, guiding updates to value functions or Q values. What is the Monte Carlo versus TD learning trade-off? Monte Carlo has low bias but high variance since it waits until episodes finish. TD has higher bias but lower variance because it updates after each step. In practice, TD is more widely used in online environments. What is the eligibility trace in RL? Eligibility traces assign credit to multiple past states and actions for a received reward. They bridge Monte Carlo and TD by allowing multi-step updates. TD lambda uses a parameter lambda to control how far back the credit is assigned. What is the role of dynamic programming in RL? Dynamic programming provides foundational algorithms like policy iteration and value iteration. While impractical for large state spaces, it introduced key ideas like Bellman equations that underpin modern model-free and deep RL methods. What is dynamic programming in reinforcement learning? Dynamic programming, DP, refers to a set of algorithms that solve MDPS using the Bellman equations. It requires a complete model of the environment, including transition probabilities and rewards. Though rarely practical at scale, DP is foundational for RL. What assumptions does DP make in RL? DP assumes that the MDP is fully known. You must know the transition function P of S prime, given S and A, and reward function R of S and A. This assumption makes DP useful for theory, but impractical in many real-world scenarios where models are unknown. What is policy evaluation in dynamic programming? Policy evaluation computes the value function VPI of ES for a given policy PI. It repeatedly applies the Bellman expectation equation until values converge. This helps estimate how good the policy is before improving it. How is policy improvement done in DP? Policy improvement chooses better actions by making the policy greedy with respect to the current value function. If Q pi of S comma A is known, we update Pi of S arrow argmax a Q pi of S comma A. Iteratively applying evaluation and improvement leads to optimal policies. What is the policy iteration algorithm? Policy iteration alternates between two steps: policy evaluation, compute VPI of S. Policy improvement, update PONI of S to maximize action values. This process repeats until the policy stops changing, guaranteeing convergence to the optimal policy. What is value iteration? Value iteration combines policy evaluation and improvement into a single update. V of S is equal to max AE of R plus gamma V of S prime. It updates values until convergence and derives the optimal policy from the final values. Value iteration is often faster than policy iteration. What is the difference between policy iteration and value iteration? Policy iteration explicitly alternates evaluation and improvement steps, while value iteration applies the Bellman optimality update directly. Both converge to the same optimal policy, but value iteration is more computationally efficient in many cases. What is generalized policy iteration, GPI? GPI is the iterative process of alternating between policy evaluation and policy improvement in any order or frequency. It generalizes policy and value iteration, showing that RL algorithms are essentially forms of GPI. How does DP guarantee convergence to optimal policies? Because the Bellman equations form contraction mappings, repeated application of updates converges to unique fixed points, the optimal value function and corresponding optimal policy. This mathematical guarantee is a core strength of DP. What are the limitations of dynamic programming in RL? Main limitations are: requires full knowledge of the environment, computationally expensive for large state or action spaces, not feasible for continuous or complex domains. These limitations motivated model-free RL methods like Q-learning. How does policy evaluation work with iterative updates? Iterative policy evaluation starts with arbitrary values and repeatedly updates V of S using V of S equals sigma pi of a given S times R plus gamma sigma P of S prime given S comma a times V of S prime. The process continues until values converge within a small threshold. What is the role of Bellman equations in DP? The Bellman expectation and optimality equations provide recursive relationships between values. DP algorithms rely on these equations to compute value functions and improve policies systematically. How do synchronous versus asynchronous DP updates differ? Synchronous updates. All states are updated in parallel at each iteration. Asynchronous updates. States are updated one at a time in arbitrary order. Asynchronous methods can be more efficient in practice and form the basis of modern RL algorithms. What is the time complexity of policy iteration? Policy iteration is computationally expensive because each evaluation step requires solving systems of equations. Its time complexity can be high for large state spaces, making it less practical than approximate methods. Why is value iteration preferred in practice over policy iteration? Value iteration avoids full policy evaluation at each step, instead applying direct updates. This makes it faster and easier to implement in many problems, especially with large state spaces. What is modified policy iteration? Modified policy iteration performs partial policy evaluation instead of full convergence at each step. It balances the efficiency of value iteration with the stability of policy iteration. How do DP methods illustrate the exploration-exploitation balance? While DP itself doesn't require exploration, since it knows the model, it conceptually highlights the need to consider all actions to compute optimal policies. This inspires exploration strategies in model-free RL. What is the curse of dimensionality in DP? As state and action spaces grow, the number of possible state-action pairs explodes, making DP computationally infeasible. This curse of dimensionality motivated approximate RL and function approximation techniques. How does DP relate to model-based RL? DP is essentially a form of model-based RL, since it assumes knowledge of the environment's dynamics. Modern model-based RL extends DP ideas by learning the model when it's unknown. Why is DP still important despite its limitations? DP is rarely applied directly in real-world RL, but it provides the theoretical backbone for modern algorithms. Concepts like Bellman equations, policy iteration, and value iteration underpin Q-learning, Actor-Critic, and deep RL. What does model-free mean in RL? Model-free methods don't require knowledge of transition probabilities or reward functions. Instead, they learn directly from experience by interacting with the environment. Popular examples include Monte Carlo, SARSA, and Q-learning. They trade efficiency for flexibility. What is model-free prediction in RL? Prediction means estimating the value function for a given policy without knowing the environment's model. Algorithms like Monte Carlo and temporal difference TD methods use sampled experiences to approximate expected returns. What is Monte Carlo prediction? Monte Carlo prediction estimates value functions by averaging the returns of many episodes generated under a policy. It requires complete episodes but doesn't need environment dynamics. It works well in episodic tasks. What is temporal difference TD prediction? TD prediction updates values based on observed rewards and estimates of future returns. It blends Monte Carlo and DP ideas, enabling learning from incomplete episodes. TD0 is the simplest and most widely used form. What is the main difference between Monte Carlo and TD methods? Monte Carlo methods wait until the end of an episode to update values, while TD methods update after each step. Monte Carlo has low bias but high variance. TD has higher bias but lower variance, making it more efficient in practice. What is the control problem in RL? Control refers to learning the optimal policy that maximizes expected rewards. Unlike prediction, which evaluates a given policy, control algorithms, like SARSA and Q-learning, continuously improve policies through interaction. What is SARSA in RL? SARSA state action. Reward state action is an on-policy TD control method. It updates Q values based on the action actually taken under the current policy. This makes it more conservative and stable in stochastic environments. What is the SARSA update rule? The update is Q of S comma A is equal to Q of S comma A plus alpha of R plus gamma, Q of S prime comma A prime minus Q of S comma A. Here, the next action A is chosen using the same policy. Example is epsilon greedy, ensuring on-policy learning. What is Q-learning? Q-learning is an off-policy TD control algorithm. It updates Q values toward the maximum possible action in the next state, regardless of the policy used to generate the action. This makes it more aggressive and often converges faster. What is the Q-learning update rule? Q of S comma A is Q of S comma A plus alpha R plus gamma max a prime Q of S prime comma a prime minus Q of S comma A. This update uses the best possible action at the next state, not the one actually taken, making Q-learning off-policy. What is the difference between SARSA and Q-learning? SARSA is on-policy, updating Q values using the action chosen by the current policy, while Q-learning is off-policy, updating toward the optimal action regardless of the behavior. SARSA is safer in noisy environments. Q-learning often achieves better performance. What is epsilon greedy exploration in RL? Epsilon greedy balances exploration and exploitation. With probability epsilon, the agent takes a random action. With probability 1 minus epsilon, it takes the greedy action. Over time, epsilon is often decayed to shift from exploration to exploitation. What is the difference between on-policy and off-policy control? On-policy methods, like SARSA, improve the same policy they follow. Off-policy methods, like Q-learning, learn an optimal policy while following a different behavior policy. Off-policy is more flexible, but harder to stabilize. What is double Q-learning? Double Q-learning reduces overestimation bias in standard Q-learning. It maintains two Q-value estimates, using one to select the action and the other to evaluate it. This improves stability and accuracy in value estimates. What is expected SARSA? Expected SARSA updates Q values using the expected value under the current policy instead of the single sampled action. This reduces variance and improves learning efficiency compared to standard SARSA. What is the main challenge of tabular Q-learning? Tabular Q-learning stores a value for every state action pair, which becomes infeasible in large or continuous state spaces. Function approximation or deep Q networks. DQNs are used to handle scalability. What is function approximation in model-free RL? Function approximation replaces tabular representations with models like linear regression or neural networks that generalize across states. This enables RL to scale to large, continuous environments, but introduces approximation errors. What is off-policy evaluation in RL? Off-policy evaluation estimates the value of a target policy using data generated from a different behavior policy. Techniques like importance sampling adjust for the distribution mismatch. This is useful for testing policies before deployment. What is importance sampling in RL? Importance sampling corrects the bias when evaluating one policy using data from another. It reweights returns by the ratio of target policy probability to behavior policy probability, making off-policy evaluation feasible. What are the strengths of model-free RL methods? They're flexible, don't require environment models, and can adapt to complex tasks. However, they're often sample inefficient and unstable compared to model-based methods. Still, algorithms like Q-learning remain core building blocks of modern RL. What is deep reinforcement learning? Deep RL. Deep RL combines reinforcement learning with deep neural networks. Neural nets are used as function approximators to handle high-dimensional or continuous state spaces, enabling RL to tackle complex problems like Atari games, robotics, and autonomous driving. What is a deep Q network, DQN? DQN uses a deep neural network to approximate the Q function instead of a Q table. Inputs are states, like raw pixels, and outputs are Q values for each action. This breakthrough allowed RL to scale to high-dimensional tasks. How did DQN impact RL research? Introduced by DeepMind in 2015, DQN achieved human-level performance on Atari games directly from pixels. It showed the power of combining RL with deep learning, sparking rapid growth in deep RL research. What are the key innovations in DQN? Two main innovations. 1. Experience replay stores past experiences and samples them randomly to break correlations. 2. Target networks stabilize training by updating a separate target Q network less frequently. What is the DQN loss function? The DQN minimizes the mean squared error between current Q values and target Q values. L equals open parenthesis, R plus gamma max, a prime Q target open parenthesis, S prime comma, a prime close parenthesis, minus Q open parenthesis, a comma, a close parenthesis squared. This aligns network updates with the Bellman optimality principle. What is double DQN? Double DQN addresses overestimation bias in Q values. It decouples action selection and evaluation. The main network selects the action, while the target network evaluates it. This improves stability and accuracy. What is dueling DQN? Dueling DQN separates state value and advantage estimation. The network has two streams, one for value V of S and one for advantage A of S, A. Combining them improves learning efficiency, especially when some actions have little impact. What is prioritized experience replay? Instead of sampling experiences uniformly, prioritize replay samples more frequently from transitions with higher TD errors. This focuses learning on more informative experiences, accelerating convergence. What is a policy gradient method? Policy gradient methods directly optimize the policy by adjusting its parameters via gradients of expected rewards. Unlike value-based methods, they handle continuous actions naturally and allow stochastic policies. What is the reinforce algorithm? Reinforce is a Monte Carlo policy gradient algorithm. It updates policy parameters proportional to the return received for an action. While simple, it suffers from high variance, often mitigated with baselines. What is the advantage function in RL? Advantage measures how much better an action is compared to the average action in that state. A of S, A equals Q of S, A minus V of S. It reduces variance in policy gradient estimates, leading to more stable learning. What is actor-critic architecture? Actor-critic combines policy-based actor and value-based critic methods. The actor selects actions, while the critic evaluates them using value functions. This balance reduces variance and bias, making it popular in modern RL. What is the difference between A2C and A3C? A2C, Advantage Actor-Critic, synchronous version where multiple agents update in lockstep. A3C, Asynchronous Advantage Actor-Critic, asynchronous version with multiple agents running in parallel, updating a global network. A 3C speeds up training and improves robustness. What is Deep Deterministic Policy Gradient DDPG? DDPG is an actor-critic algorithm for continuous action spaces. It uses deterministic policies and combines ideas from DQN, like target networks and replay buffer, with policy gradients, enabling control in robotics and simulations. What is twin delay DDPG TD3? TD3 improves DDPG by addressing overestimation and instability. It uses twin critics, delayed policy updates, and noise regularization. This leads to more stable training in continuous action domains. What is Soft Actor Critic SAC? SAC is an off-policy actor-critic algorithm that maximizes both reward and entropy. By encouraging exploration through entropy regularization, SAC achieves state-of-the-art results in continuous control tasks. What is Trust Region Policy Optimization, TRPO? TRPO is a policy gradient method that ensures updates don't deviate too far from the old policy by constraining the KL divergence. This improves stability but can be computationally expensive. What is Proximal Policy Optimization, PPO? PPO simplifies TRPO by clipping probability ratios in the objective function. This avoids overly large policy updates while keeping optimization efficient, making PPO one of the most widely used RL algorithms today. What is Generalized Advantage Estimation, GAE? GAE is a method to reduce variance in policy gradient algorithms by adjusting how much past rewards influence advantage estimates. It balances bias and variance with a lambda parameter, improving actor-critic methods. How do recurrent networks help in deep RL? Recurrent networks like LSTMS handle partial observability by maintaining memory of past states. This is crucial in environments where the agent doesn't see the full state, like dialogue systems or financial markets. What is distributional RL? Distributional RL models the full distribution of returns instead of just the expectation. Algorithms like C51 and QRDQN improve accuracy by capturing uncertainty, leading to better decision-making in high-variance environments. What is NoisyNet in RL? NoisyNet introduces parameterized noise into neural network weights, enabling exploration through stochasticity in the network itself. This replaces epsilon-greedy exploration and improves learning efficiency. What is Rainbow DQN? Rainbow combines multiple DQN improvements: double DQN, dueling DQN, prioritized replay, distributional RL, and noisy nets. Together, they form a powerful benchmark algorithm for discrete control tasks. What is hierarchical reinforcement learning, HRL? HRL decomposes tasks into subtasks or options. The agent learns high-level policies that decide which low-level sub-policies to execute. This makes solving long-horizon problems more tractable and interpretable. What is curiosity-driven exploration in deep RL? Curiosity-driven agents reward themselves for reducing prediction error about the environment. This encourages exploration even when external rewards are sparse, improving learning in challenging environments. What is multi-agent deep RL? Multi-agent deep RL extends RL to environments with multiple interacting agents. Agents may cooperate, compete, or both. Applications include autonomous driving, distributed robotics, and resource allocation. What is imitation learning in RL? Imitation learning trains agents by mimicking expert demonstrations. Instead of learning purely from rewards, the agent learns policies from labeled trajectories. It's useful when rewards are hard to define, such as teaching robots from human actions. What is inverse reinforcement learning, IRL? IRL infers the reward function from expert demonstrations. Instead of replicating actions, it uncovers the underlying motivations. IRL is applied in robotics, healthcare, and safety-critical applications, where designing rewards is difficult. What is meta-reinforcement learning? MetaRL trains agents to learn how to learn. The idea is to develop agents that adapt quickly to new tasks with limited data by leveraging prior experience. This is critical for generalizing across environments. What are some real-world applications of DeepRL? DeepRL is applied in robotics, like locomotion, manipulation, finance, like trading strategies, healthcare, like treatment planning, games like AlphaGo, Dota 2, recommendation systems, and autonomous driving. Its ability to scale to high-dimensional spaces makes it transformative. What is the actor-critic method in RL? The actor-critic method combines two elements: the actor, which updates the policy directly, and the critic, which evaluates actions using value functions. This approach reduces variance compared to pure policy gradients and provides stable updates. What are the advantages of actor-critic over value-based methods? Actor-critic handles continuous action spaces naturally, learns stochastic policies, and reduces variance with critic feedback. It also supports scalable architectures, making it more powerful than purely value-based algorithms like Q-learning. What is the main drawback of actor-critic methods? Actor-critic methods can be unstable due to the critic's approximation errors. If the critic is poorly trained, the actor may receive misleading feedback. Stabilization techniques like entropy, regularization, and trust regions are often required. What is Advantage Actor-Critic A2C? A 2C improves on standard actor-critic by using the advantage function A of S comma, A equals Q of S comma, A minus V of S. This reduces variance and improves learning efficiency, making it one of the most commonly used baselines in RL. What is Asynchronous Advantage Actor-Critic A3C? A 3C runs multiple agents in parallel across environments, each updating a shared global model asynchronously. This increases training speed, improves exploration, and stabilizes learning compared to single-threaded actor-critic. What is the key difference between A2C and A3C? A 2C is synchronous. Agents update together in lockstep. A 3C is asynchronous, allowing agents to update independently. While A3C speeds up training, A2C is easier to implement with modern parallel hardware like GPUs. What is the Deep Deterministic Policy Gradient DDPG algorithm? DDPG is an off-policy actor-critic algorithm for continuous actions. The actor outputs deterministic actions, and the critic evaluates them. Inspired by DQN, it uses target networks and replay buffers for stability. What is the limitation of DDPG? DDPG suffers from overestimation bias, instability, and sensitivity to hyperparameters. It also struggles with exploration since it uses deterministic policies. Enhancements like TD3 and SAC were developed to address these issues. What is twin-delayed DDPG TD3? TD3 improves DDPG with three techniques. 1. Twin critics to reduce overestimation bias. 2. Delayed policy updates for more stable learning. 3. Target policy smoothing by adding noise. Together, these make TD3 more reliable in continuous control tasks. What is Soft Actor Critic SAC? SAC adds entropy maximization to the objective, encouraging exploration and robustness. It learns stochastic policies in an off-policy setting, achieving state-of-the-art results in continuous environments like robotics. How does entropy regularization help actor-critic methods? Entropy regularization encourages policies to remain stochastic instead of collapsing too quickly to deterministic actions. This promotes exploration, reduces premature convergence, and improves sample efficiency. What is the difference between deterministic and stochastic policies in actor-critic? Deterministic policies, DDPG, TD3, output a single action for each state, while stochastic policies, A2C, SAC, output probability distributions. Stochastic approaches handle uncertainty better and encourage exploration. What is Trust Region Policy Optimization, TRPO, in actor-critic? TRPO constrains updates by limiting KL divergence between old and new policies. This ensures stable improvement, preventing large, destructive policy updates. However, it is computationally heavy. What is proximal policy optimization, PPO, in Actor-Critic? PPO simplifies TRPO by clipping the probability ratio in the objective. It achieves stability while being computationally efficient, making it one of the most popular Actor-Critic algorithms today. What is generalized advantage estimation, GAE? GAE improves advantage estimation in Actor-Critic by balancing bias and variance with a lambda parameter. It smooths policy updates and improves sample efficiency, especially in PPO and A2C. How does Actor-Critic handle continuous action spaces? The actor outputs continuous distributions, like Gaussian means and variances, from which actions are sampled. This makes Actor-Critic ideal for tasks like robotics, where discrete actions aren't sufficient. What is the natural policy gradient method? Natural policy gradient preconditions updates with the Fisher information matrix, ensuring updates move in directions that respect the geometry of the policy space. This improves stability compared to vanilla gradients. What are multi-agent Actor-Critic methods? They extend Actor-Critic to environments with multiple agents that may cooperate or compete. Examples include MADDPG, which stabilizes training by conditioning critics on global information. What are some applications of Actor-Critic methods? They're used in robotics, continuous control, finance, portfolio management, recommendation systems, autonomous driving, and real-time decision-making systems like energy optimization and traffic control. Why are Actor-Critic methods considered the backbone of modern deep RL? Actor-Critic combines the strengths of value-based and policy-based methods, scales to continuous domains, supports modern optimizations like PPO and SAC, empowers state-of-the-art applications in real-world RL. Why is exploration important in RL? Exploration ensures agents discover better strategies instead of sticking to suboptimal ones. Without it, they may exploit known actions prematurely. Balancing exploration with exploitation is key for achieving optimal long-term performance. What is epsilon greedy exploration? Epsilon greedy selects a random action with probability epsilon and the best known action otherwise. Over time, epsilon is decayed to shift from exploration to exploitation. It's simple, effective, and widely used in Q-learning. What is softmax, Boltzmann exploration? Softmax assigns probabilities to actions based on their estimated values using a temperature parameter tau. Higher tau increases randomness, while lower tau makes the agent greedier. It allows smoother exploration compared to epsilon greedy. What is upper confidence bound UCB exploration? UCB selects actions based on both their estimated value and uncertainty. It balances exploration and exploitation by favoring actions with high potential reward or high uncertainty, commonly used in multi-arm bandit problems. What is Thompson sampling? Thompson sampling samples actions based on their probability of being optimal using Bayesian inference. It naturally balances exploration and exploitation and often outperforms epsilon greedy in bandit and RL tasks. What is optimistic initialization in RL? Optimistic initialization sets initial Q values high, encouraging the agent to explore since most actions initially appear promising. Over time, estimates correct, but exploration ensures diverse state action coverage. What is the difference between directed and undirected exploration? Undirected exploration, random actions like epsilon greedy. Directed exploration, actions chosen deliberately to maximize information gain or reduce uncertainty, like curiosity-driven or count-based methods. Directed exploration is generally more efficient. What is count-based exploration? Count-based exploration assigns bonuses to less visited states, encouraging the agent to explore novel areas. While easy in discrete spaces, adaptations like pseudo-counts extend it to high-dimensional environments. What is curiosity-driven exploration? Curiosity-driven methods reward the agent for reducing prediction errors about the environment. This intrinsic motivation helps agents explore environments where external rewards are sparse or delayed. What is intrinsic motivation in RL? Intrinsic motivation provides internal rewards for exploration, novelty, or learning progress, rather than relying solely on external rewards. It makes agents more autonomous and effective in sparse reward tasks. What is the exploration-exploitation dilemma? The dilemma is the trade-off between exploring new actions for potential long-term gains and exploiting known actions for immediate rewards. An effective RL strategy must balance both dynamically. What is entropy-based exploration? Entropy-based exploration maximizes the randomness of action distributions. Algorithms like soft actor-critic encourage high-entropy policies to avoid premature convergence and improve robustness. What is posterior sampling and exploration? Posterior sampling, Bayesian RL, selects policies by sampling from a posterior distribution over models. This naturally incorporates uncertainty and balances exploration with exploitation. How does exploration differ in discrete versus continuous action spaces? In discrete spaces, random or epsilon-greedy exploration is easy. In continuous spaces, exploration often involves adding noise, like Gaussian or Ornstein-Uhlenbeck noise, to policy outputs for variability. What is Ornstein-Uhlenbeck noise in RL? OU noise generates temporally correlated exploration noise, making it suitable for continuous control tasks like robotics. It was famously used in the DDPG algorithm to improve exploration stability. What is parameter noise in exploration? Parameter noise perturbs the agent's network weights instead of adding noise to actions. This leads to consistent exploration strategies and often outperforms action noise in deep RL. What is the explore then commit strategy? Explore then commit first explores randomly for a set number of steps, then commits to exploiting the best known policy. It's simple but often inefficient compared to adaptive strategies like UCB. What is the role of Bayesian methods in exploration? Bayesian methods model uncertainty explicitly, guiding exploration toward actions with uncertain outcomes. Techniques like Thompson sampling and posterior sampling are Bayesian approaches widely applied in RL. What are novelty-based exploration methods? Novelty-based methods give intrinsic rewards for visiting new or diverse states. Examples include random network distillation, RND, and pseudocounts. These approaches encourage agents to discover unvisited regions of the environment. What are the main challenges of exploration in RL? Challenges include balancing exploration with exploitation, handling sparse or deceptive rewards, scaling to high-dimensional spaces, and ensuring safe exploration in real-world domains where random actions may be risky. How is RL applied in robotics? In robotics, RL helps agents learn control tasks like locomotion, grasping, or navigation. Algorithms such as DDPG, PPO, and SAC enable robots to adapt to dynamic environments, reducing reliance on handcrafted control rules. How does RL power autonomous driving? RL trains self-driving cars to make sequential decisions in uncertain environments, such as lane changing or obstacle avoidance. By optimizing for long-term safety and efficiency, RL complements rule-based and supervised approaches. How is RL used in healthcare? In healthcare, RL assists in personalized treatment plans, drug discovery, and scheduling. For example, RL agents can recommend chemotherapy dosages by maximizing long-term patient health outcomes under uncertainty. How does RL apply to finance? Finance uses RL for portfolio optimization, trading strategies, and risk management. Agents learn to balance risk and return dynamically, adapting to market changes. Deep RL is especially promising for algorithmic trading. How is RL applied in recommendation systems? RL optimizes for long-term user engagement, not just immediate clicks. By modeling recommendations as sequential decision-making, RL improves personalization in platforms like YouTube, TikTok, and Netflix. How is RL used in supply chain management? RL agents optimize logistics, demand forecasting, and inventory control by learning adaptive policies that minimize costs and maximize service levels, especially in uncertain and fluctuating markets. How does RL help in natural language processing, NLP? RL is used in tasks like dialogue systems, text summarization, and machine translation. For instance, RL fine-tunes large language models by optimizing reward signals, such as human feedback or BLEU scores. How does RL apply to energy management? RL optimizes energy usage in smart grids, buildings, and renewable systems. Agents balance supply and demand, reduce energy costs, and improve sustainability by learning adaptive control strategies. How is RL used in game playing? RL has achieved landmark successes in games. AlphaGo, AlphaZero, and OpenAI's Dota 2 agents. These systems combine RL with search and deep networks to outperform humans in highly complex environments. How is RL used in industrial process control? RL optimizes operations in manufacturing, chemical plants, and production lines. Agents continuously adjust controls to improve efficiency, reduce waste, and maintain safety under varying conditions. How does RL apply to adaptive traffic signal control? RL agents optimize traffic lights to minimize congestion and waiting time. By learning from real-time traffic flow data, they adapt signal timings dynamically, improving urban mobility. How is RL applied in education technology? In EdTech, RL personalizes learning paths for students. Agents recommend exercises or lessons based on student progress, maximizing long-term knowledge retention and engagement. How is RL used in cloud computing? RL optimizes resource allocation, load balancing, and job scheduling in cloud environments. By learning adaptive strategies, agents reduce latency, cut costs, and ensure scalability. How does RL apply in personalized medicine? RL tailors treatment strategies to individual patients by considering sequential outcomes. For example, it can optimize insulin dosages in diabetes care by maximizing long-term health. How is RL used in cybersecurity? RL helps in intrusion detection, adaptive defense, and automated response systems. Agents learn to predict and counter evolving cyber attacks in real time. How does RL support dialogue agents and chatbots? RL fine-tunes conversational agents by rewarding meaningful, helpful, or engaging responses. Techniques like RLHF, reinforcement learning from human feedback, make systems like ChatGPT more aligned with user preferences. How is RL applied in space exploration? RL optimizes spacecraft trajectory planning, planetary rovers, and autonomous navigation in unknown terrains. It enables adaptive decision-making where pre-programmed strategies may fail. How does RL contribute to personalized marketing? RL agents decide the timing, content, and channel of ads or offers. By optimizing long-term customer engagement, RL improves conversion rates and customer satisfaction. How is RL used in anomaly detection? RL agents learn normal behavior patterns in systems like networks, finance, or manufacturing. Deviations trigger anomaly alerts, helping detect fraud, faults, or failures early. How is RL applied in multi-agent systems? RL enables cooperation and competition in multi-agent settings like swarm robotics, auctions, or autonomous fleets. Agents learn adaptive strategies that balance individual goals with collective objectives. What are the main challenges in reinforcement learning? Challenges include sample inefficiency, instability, reward design, safety concerns, scalability to large environments, and the difficulty of transferring learned policies across tasks. Balancing exploration and exploitation also remains a core issue. Why is sample inefficiency a problem in RL? RL often requires millions of interactions to learn effective policies, which is impractical in real-world domains like robotics or healthcare. Improving sample efficiency through model-based methods or offline RL is an active research area. Why is stability a challenge in RL training? RL involves non-stationary data because the agent's behavior changes as it learns. Combined with function approximation, this can cause instability or divergence. Techniques like replay buffers and target networks help mitigate this. Why is reward design difficult in RL? Poorly designed rewards can lead to unintended behaviors, like agents exploiting loopholes instead of solving the task. Crafting reward functions that align with real-world goals while avoiding exploitation is a major challenge. What is the sparse rewards problem in RL? Sparse rewards occur when agents receive feedback infrequently, making it difficult to learn. For example, winning a game may provide a reward only at the end. Shaping rewards, intrinsic motivation, and hierarchical RL help address this. What is catastrophic forgetting in RL? Catastrophic forgetting happens when agents overwrite old knowledge while learning new tasks. This makes it hard to transfer or maintain skills across multiple environments. Continual learning strategies aim to reduce this issue. What is the sim to real gap in RL? Agents trained in simulations often fail in the real world due to mismatches in dynamics. Domain randomization, transfer learning, and robust policies are used to bridge the sim to real gap. Why is safe exploration a challenge in RL? Exploration can be risky in real-world settings like healthcare or autonomous driving. Agents must balance learning with safety constraints to avoid harmful or irreversible actions. This makes safe RL a crucial research area. How do partial observability issues affect RL? In many environments, agents cannot observe the full state. Example is autonomous cars with limited sensors. This violates the Markov property, requiring solutions like recurrent networks, belief states, or POMDP formulations. Why is scaling RL to large state action spaces challenging? As complexity grows, the number of possible states and actions explodes, making it hard to explore effectively. Function approximation and hierarchical methods are used, but scalability remains a challenge. What is the problem of overestimation bias in RL? Algorithms like Q-learning tend to overestimate action values, leading to suboptimal policies. Double Q-learning and twin critics, as in TD3, are designed to reduce this bias. What is credit assignment in RL, and why is it difficult? Credit assignment is determining which past actions led to a reward. In long horizon tasks, rewards may appear much later than the relevant action, making it hard for agents to attribute success or failure correctly. What is non-stationarity in multi-agent RL? In multi-agent settings, the environment changes as other agents adapt, making it non-stationary. This complicates learning since the optimal policy is constantly shifting. Centralized training and decentralized execution approaches help mitigate it. How do computational costs challenge RL adoption? Deep RL requires massive computational resources for training, often using clusters of GPUs or TPUs. This high cost limits accessibility and slows progress in practical applications. Why is explainability a challenge in RL? Deep RL policies, often based on neural networks, act as black boxes. Lack of transparency makes it hard to trust or debug agents, especially in safety-critical domains like healthcare or finance. What is the challenge of generalization in RL? Agents often overfit to training environments and fail to generalize to new conditions. Domain adaptation, meta-learning, and robust training techniques are active areas of research to improve generalization. Why is multi-objective optimization hard in RL? Many tasks require balancing multiple objectives, like speed versus safety. Standard RL optimizes a single reward signal, making it challenging to handle trade-offs without advanced frameworks like multi-objective RL. How do adversarial attacks threaten RL systems? Adversarial perturbations to inputs or environments can fool RL agents into making poor decisions. Ensuring robustness against such attacks is an emerging security concern. Why is offline RL challenging? Offline RL trains agents from pre-collected datasets without further interaction. The challenge lies in distribution shift. The agent may try out-of-distribution actions, leading to unreliable estimates and poor performance. What are the ethical challenges in deploying RL? Ethical issues include unintended bias, safety risks, misuse in autonomous weapons, and lack of accountability for harmful decisions. Ensuring responsible and transparent deployment is critical as RL moves into real-world systems. What are the major future directions in RL research? Future directions include scaling RL to real-world domains, improving sample efficiency, integrating model-based and model-free methods, safe RL, explainability, and combining RL with large language models and multimodal systems. How will model-based RL evolve in the future? Model-based RL is expected to play a bigger role since it improves sample efficiency by simulating future outcomes. Advances in world models and generative modeling will enable RL agents to plan more effectively in complex environments. What is the role of meta-reinforcement learning in the future? Meta-RL enables agents to learn how to learn. Future systems will leverage past experiences to adapt quickly to new tasks with minimal data. This is critical for general intelligence and real-world adaptability. How will RL integrate with large language models, LLMs? LLMs can provide reasoning, generalization, and common sense knowledge, while RL adds sequential decision-making and optimization. Together, they'll enable conversational agents, adaptive tutoring systems, and planning-oriented AI assistants. What is the role of hierarchical RL in the future? Hierarchical RL will help solve long-horizon problems by decomposing tasks into subtasks. This will be especially useful in robotics, autonomous driving, and multi-step planning systems where simple end-to-end learning is inefficient. How will multi-agent RL develop in the future? Future MIRL research will tackle scalability, coordination, and fairness across large groups of agents. Applications include autonomous fleets, smart cities, and collaborative robots. These systems will balance cooperation and competition dynamically. What are the prospects of safe reinforcement learning? Safe RL will become critical for real-world adoption. Future systems will integrate formal safety guarantees, human oversight, and risk-sensitive policies to ensure reliability in healthcare, finance, and autonomous systems. How will explainability in RL improve in the future? Future RL will focus on interpretable policies with human-understandable reasoning. This may include causal reasoning, visual explanations, or natural language summaries of agent behavior, increasing trust in critical applications. What role will offline and batch RL play in the future? Offline RL will allow agents to learn from large pre-collected datasets without costly or risky online exploration. It will be essential in domains like healthcare, where trial and error in the real world is unsafe. What is the ultimate vision for reinforcement learning in AI? The ultimate vision is creating general-purpose agents that learn efficiently, act safely, adapt rapidly, and collaborate with humans. RL will be a cornerstone in building autonomous systems that go beyond narrow tasks toward true artificial general intelligence, AGI. Congratulations! You've just completed 200 expert-level reinforcement learning interview questions and answers. From fundamentals to deep RL and future directions, you now have the insights to shine in interviews and projects. If this helped you, don't forget to like, subscribe, and hit the bell for more AI and ML content. Share your toughest RL question in the comments, and I'll cover it in a future video.